The general mole balance equation. To perform a mole balance on any system, the system boundaries must first be specified. The volume enclosed by these boundaries is referred to as the system volume. We shall perform a mole balance on species J in a system volume where species J represents the particular chemical species of interest. A mole balance on species J at any instant in time t yields the following equation. The rate of flow of J into the system in moles per unit of time minus the rate of flow of J out of the system in moles per unit of time plus the rate of generation of J by chemical reaction within the system in moles by units of time is equal to the rate of accumulation of J within the system in moles by units of time. So we will have that in minus out plus generation is equal to accumulation. What is coming in is the mole flow rate of J is Fj0. What is going out is Fj. What is generated is Gj. And what is accumulated is dnj divided by T. Nj represents the number of moles of species J in the system at time T. If all the system variables, temperature, catalytic activity, concentration of the chemical species are spatially uniform to the system volume, the rate of generation of species J, which we are going to call Gj, is just the product of the reaction volume, B, and the rate of formation of species J that we are going to call Rj. So we will have that Gj is equal to Rj times B. The units in the left will be moles by second by example, and the units on the right will be for the rate moles by second by liters and the volume in liters. So we will have that at the end we will have moles by seconds in both sides of the equation. A basic equation for chemical reaction engineering is Fj0 minus Fj plus the integral of Rj dV is equal to dnj divided by dt. From this general mole balance equation, we can develop the design equations for the various types of industrial reactors: batch, semi-batch, and continuous flow. Batch reactors. A batch reactor is used for a small-scale operation, for testing new processes that have not been fully developed, for the manufacture of expensive products, and for processes that are difficult to convert to continuous operations. And here we have a batch reactor. At the top of the reactor, we have the entrance of the reactants. At the bottom of it, we have the exit of the product. And inside the reactor, we have systems to mix the reactants. A batch reactor has neither inflow nor outflow of reactants or products while the reaction is being carried out. So Fj0 equal to Fj equal to 0. Nothing is coming in, nothing is going out. The resulting general mole balance on species J is dnj divided by dt is equal to the integral of Rj dV. If there is no variation in the rate of reaction throughout the reactor volume, we can take Rj out of the integral and write the mole balance in the form dnj divided by dt equal to Rj times B, because Rj is constant and we took it out of the integral. Let's consider the summarization of species A in a batch reactor. So A goes to B. As the reaction proceeds, the number of moles of A decreases and the number of moles of B increases. We might ask ourselves what time T1 is necessary to reduce the initial number of moles from Na0 to a final desired number Na1. And here we have the plots. At the left, we have that Na starts at Na0 and decreases with time until at time T1 reaches a number of Na1. And for the product, we have that the product B starts at 0 at time 0 and goes increasing until it reaches a number of NB1 at time T1. Applying the equation for the mole balance for a substance A, we will have that dNA divided by dt is equal to Ra times B. If we rearrange this equation, we will have that dt is equal to dNA divided by Ra times B. If we integrate with the limit that at time t equals 0, then Na is equal Na0, and at time t equal T1, then Na equal Na1, we will have that T1 is equal to the integral from Na1 to Na0 of dNA divided by minus Ra times B. And here we must notice that the limits of the integrals are from Na1 to Na0 and not from Na0 to Na1 because we introduce the minus sign in the rate, so we change the limits. And this equation is the integral form of the mole balance on a batch reactor. It gives the time T1 needed to reduce the number of moles from Na0 to Na1 and also to form NB1 moles of B.